Hi everyone, today I'll be walking you through reaction 8, which is a base-promoted carbon-carbon bond-forming reaction. Specifically, it's a Michael addition reaction followed by an acidic workup. I'll start by identifying the key players. First, we'll start with the electrophile and the nucleophile. In this reaction, LDA is used to depronate the alpha hydrogen of the starting ketone, forming an enolate. This enolate is our nucleophile. It has a negatively charged alpha carbon that can attack electrophilic centers, and the electrophile in this case is the alpha-beta unsaturated carbonyl compound, also known as an enone. The beta carbon of the enone is electrophilic due to the conjugation with the carbonyl group. In the next section, we'll talk about the curved arrow mechanism. Here's how the mechanism works step by step. So the first step, LDA deprotonates the alpha carbon of the starting ketone to form a resonance-stabilized enolate. Step 2, the enolate then performs a 1,4 conjugate addition, also known as the Michael addition, to the beta carbon of the enone. This forms a new C-C bond. In step 3, the enolate formed after the attack picks up a proton during the acidic workup, yielding a beta keto alcohol. This mechanism involves the flow of electrons from the enolate or nucleophile to the beta carbon of the enone electrophile, and the pi electrons of the double bond shifting to the alpha carbon, eventually forming a new enolate, which is then protonated. In the next section, we'll talk about electron flow explanation. In the first step, LDA abstracts a proton, and the electrons from that CH bond shift to form the enolate. In the next step, the lone pair on the alpha carbon attacks the electrophilic B carbon, forming a new sigma bond and pushing the pi electrons onto the alpha carbon of the enone. The final protonation restores neutrality. In the regiochemical and stereochemical preferences section, regiochemically, this reaction is highly selective for 1,4 addition rather than 1,2 addition, because the conjugated system stabilizes the intermediate. This preference is driven by the thermodynamic stability of the enolate intermediate and the ability to form a more stable resonance-stabilized product. Stereochemically, since the reaction forms a new stereocenter, a mixture of enantiomers may be formed unless a chiral catalyst or reagent is used, but that's not shown here. The electron flow involves the movement of electrons from the CH bond to form the C-C double bond in the enolate, then from the enolate's double bond to attack the carbonyl carbon, and finally from the carbonyl double bond to the oxygen. The oxygen is then protonated. Again, the reaction shows regioselectivity. The nucleophile attacks the carbonyl carbon, leading to addition of the hydroxyl group at a specific position. There is no stereochemical preference shown in the product. The product is not chiral. The reaction is a base-catalyzed addition of a hydroxyl group to a cyclic ketone. The LDA acts as a base to form an enolate, which then attacks the carbonyl group. Acidic workup protonates the oxygen. The reaction is regioselective but not stereoselective. LDA, being a strong base, abstracts a proton from the alpha carbon of the ketone, forming an enolate ion. The electrons from the CH bond move to form a CC double bond. The enolate ion acts as a nucleophile, attacking the electrophilic carbonyl carbon. The electrons from the CO double bond move to the oxygen atom. After acidic workup, or protonation, a hydroxyl group is added to the molecule. To wrap up, this is a classic example of carbon-carbon bond formation via a Michael addition, using LDA as a strong base to generate a nucleophilic enolate, which attacks an AB unsaturated carbonyl compound, followed by an acidic workup to form a stable product with new carbon-carbon and carbon-oxygen bonds. Again, in this reaction, the electrophile is the carbonyl group CO double bond of the cyclic ketone. The nucleophile is the LDA, a strong base that acts as a nucleophile in this case.